All right, we're going to do 7.3 partial fractions. And I must say, as far as this chapter goes, this is probably the section that's going to give you the most trouble and take you the most time to wrap your mind around it and really get the concept. Because of this, I'm going to give you notes today and ask you to practice. And then tomorrow I'm going to ask you to just do an extra worksheet just on these to practice them. But I can't stress enough, the more you practice them, the easier these will get. Okay, so partial fractions. Think about, I have a fraction like 1 over x plus 1 over x squared plus maybe 1 over x minus 4, okay? If those fractions were given to you, you would say, well, to add them together, I need a common denominator. Let's see. I have x and I have x squared. So if I put an x squared, that'll cover both the first two. But x minus 4 is completely different, so that's another factor. So I get a common denominator of like x squared times x minus 4. And then I would get this fraction on the top, okay? I'd get numbers up there. Now, I'm not going to do all the work to get there. What we are going to do today is we're going to start with this fraction, the answer, and work our way backwards to what the numerators could have been on the separate fractions. We're going to what we call like decompose the bigger fraction and say what could have gotten us this answer. Okay, that's our job. So we have 4 different scenarios we're going to look at. The first one, the denominator is a product of distinct linear factors. So they're only x's. They're not x squareds or anything like that. They're just singular powers, and they're different factors, distinct. Okay, I'll kind of point that out as we get to it. The second scenario is we still have all linear factors, but some of those are repeated more than once, and we have that issue. Then we have some on number 3 where we have some quadratic factors. Those are to the power 2 to start with, and none of them are repeated. Or the fourth one where we have quadratics, again, something to the second power, and they are repeated. Okay, so these are the scenarios we're going to look at and we're going to work through so you can see these. Okay. So number 1, set up the partial fraction decomposition with the unknown constants a, b, c, etc. in the numerators of the decomposition. Okay, I want to just put kind of a note first. If needed, okay, because sometimes you need this. If needed, factor the denominator. Okay, and I'm going to put this here, and then I'm going to tell you that none of my examples need this done, but you might get to something on your homework that you do need to factor first. So if needed, factor your denominator, because what's important is we need factors in our denominator, not just a polynomial. Okay, we need factors. Okay, so we're going to set up our partial decomposition with the unknown constants in the numerators, and then we're going to work from there. So let me kind of walk you through this first one, kind of following these steps as best we can so you kind of see what they're talking about. So number 1, this first example is the number 1 scenario. This is a denominator. It's been factored for us, and each of these factors are very different. I have an x minus 1, and an x plus 3. Each one of them by themselves is linear because there's no power on the x. Okay, so what we're going to do is we're going to split this fraction up into 3 fractions, 1 for the x, 1 for the x minus 1, and 1 for the x plus 3, okay? So here's the deal. We don't know what's on top. So on the top one, the first one, I'm going to say it has a denominator of a, the second one has a denominator of b, and the last one has a denominator, completely saying that wrong. All of them have numerators of a and b and c. Okay, so I've taken my fraction I'm given, and I've split it up into the 3 fractions I think were added together to make this fraction. Okay, I've decomposed them. I don't know their numerators. So in any type of rational equation, which is what we've turned this into, I don't like to work with fractions. So what I do is I multiply by the common denominator. So I'm going to multiply this entire equation now by its common denominator of x times x plus 1 times x plus 3. Okay? So when I do this, okay, and I'm going to overdo this next step a lot, okay? So you don't have to show this work every time, but I really want you to see what's happening. So what I have right now on this first one is I have 4x squared plus 13x minus 9 on the left times x plus, you know what, that's a minus 1 times x plus 3. I'll fix that here in a little bit. All over x times x minus 1 times x plus 3. okay? Then I have a up here on top times x plus 1 times x plus 3 all over x. Then I have b times x plus 1. Okay, I need to fix my typo because I'm messing myself up. Okay. This is not x plus 1. This is x minus 1, which makes this one x minus 1. There we go. Okay, so b is times x minus 1 times x plus 3 all over x minus 1. And then my last term, c, is going to be times x minus 1 times x plus 3 all over x plus 3. Okay, that's what I do when I multiply a rational equation times its denominator. I'm multiplying everything there. Now what's nice is this x cancels with that, x minus 1 cancels with this cancels, and I'm left with 4x squared plus 13x minus 9, okay? I have no more denominator on the left side. On the right side, for the a term here, my x's cancel, and I'm going to be left with a times, by the way, I'm going to FOIL that out right there, x squared, that gives me a plus 3x and minus 1x, plus 2x minus 3, okay, because I have those last two left. Then I'm going to have b over here. Well, my x minus 1's cancel, so what's left is x squared plus 3x. And finally, my x plus 3's cancel, and my c is left times x squared minus x, okay? Now, I did a little extra work there on that right side to save myself a line of work, okay? Are we following where I got rid of all my denominators and how I'm left with what I'm left with? Okay? So on my right side now, I'm going to distribute my a, b's, and c's into my parentheses. So I get a x squared plus 2ax minus 3a. Over here, I get bx squared plus 3bx. And finally, on my last one, I get plus cx squared minus cx. Okay? All right, now I want to join, kind of group at least like terms. So I have an ax squared, I have a bx squared, I have a cx squared. Okay, I pull all those to the front. For my x's, I have a plus 2ax, I have a plus 3bx, and I have a minus cx. And then the only thing I haven't used, right, is this minus 3a, okay? So here's what I have when I group like terms together. Okay, I know I'm not using the left side, and to be honest, I'm just going to leave it hanging for a little bit. Okay, so if you understand kind of here, all of these have an x squared, which leaves us with a plus b plus c when I factor out that GCF. On these three right here, I'm going to factor out a positive x, and that's going to leave me a positive 2a plus a 3b minus a c. And then I have minus 3a, okay? And again, I let it go for a little bit, but on the left side, this all still equals 4x squared plus 13x minus 9. Now what we can do is take what we have and set up a system. So here we go. What's connected to my x squared over here can be equal to what my x squared is connected to over here. So that means that a plus b plus c can equal 4. And whatever's connected to my x right here can be connected to what, or equal to what's connected to my x on this side, because we have equal sides. So I can have 2a plus 3b minus c equal to 13. And likewise, on my constants with no x's involved, my negative 3a is going to equal my negative 9. Okay? What works out super nice for me right now is I know with this very last one, my a is going to equal 3 when I solve that. Okay? I still have a system. I'm just now, whatever method works, I'm going to solve it. Notice my equations 1 and 2, if I add those together right now, I'm going to get 3a plus 4b, my c's cancel, equals 17. But what's super nice is I already know what a equals, so I'm going to plug it in. 3 times 3 plus 4b equals 17. That gives me a 9 plus 4b equals 17. Subtract 9, 4b equals 8, and b equals 2. Choose any equation I want. I'm going to take that top one of this top one over here anyways. A plus b plus c equals 4, and I already know a is 3. I know b is 2, and my c I don't know. I'm going to subtract that 5, and c equals -1. All right. Now that I know my a, my b, and my c, I can finish out my problem and say, what is the partial fraction decomposition? That means, let me put it in another color so we can see it, that I added the fractions. This a is going to go in this a spot. So I had the fraction 3 over x plus the fraction, my b is getting replaced here, 2 over x minus 1 plus the fraction -1 over x plus 3. When I added those three fractions together, it equals this big 4x squared plus 13x minus 9 over x times x minus 1 times x plus 3. We broke that fraction down into three fractions that when added together will give us that equation. So if you wanted to now work to find a common denominator between these three and do all the math and change all the numerators and do all the like terms, that's what you're going to get. So we took what was already added together and we broke it down into what things it could be to add back up to that equation. Okay? Now, I keep saying can, we could, that type of thing, because this isn't the only three fractions that would ever give you that answer. But this is probably the simplest three fractions that would give you that answer. So there are other answers out there, but this is one partial fraction decomposition of that big fraction. Okay, so let's go on and try some of the other scenarios so that we understand the rules for the other scenarios. So my next one, I have in my denominator again, thankfully again the denominator is factored. If it's not, factor it first and then go from there. So on this one, I have factors of x and x plus 7. But x plus 7 is used twice because of that squared. I want to stress this. This is not a quadratic. This is the factor x plus 7 used twice. Okay? A quadratic would have to have the x squared inside that parenthesis. That would make it a quadratic. Okay, so what I have here is I might have a fraction with just x in the denominator. And then I can have a fraction of x plus 7 once and a fraction of x plus 7 twice. Okay? And that is so important that if you have something repeated, you have to put it for every multiple it can be repeated. So if it was, I'm just giving you this hint. Say it said x plus 7 to the 5th. You'd have to have a fraction with x plus 7 underneath. You'd have to have a fraction with x plus 7 squared. You'd have to have a fraction with x plus 7 cubed. You'd have to have a fraction with x plus 7 to the 4th. And one with x plus 7 to the 5th in the denominator. Okay? So every time, if it's more than once, you have to list it in each individual and step it up until you reach the power it is. Okay? Because we don't know if it was just x times x plus 7 squared, or if there was an x plus 7 in that step as well. Okay, so just kind of giving you this hint, you've got to make sure you cover all your bases when you do this. Now, because everything's linear again, we're just going to put on top A, B, and C to stand for whatever that numerator is that we don't know about right now. Just like the last time, we're going to multiply by its common denominator of x times, and I'm going to write this way, x plus 7 times x plus 7. That covers the squared, but also the individual time, okay? So if you're okay with me not writing this times every fraction, okay, I know on the first fraction it cancels, so I'm going to be left with 3x squared plus 49. On the fraction with a, the x's cancel, but I'm still going to have a times the x plus 7 times x plus 7, or x plus 7 squared. For my b, one of the x plus 7's cancels, but I'm still left with x times x plus 7. And for my c, both of the x plus 7's cancel, but I'm still have this c times the x. All right, let me get this random extra parenthesis out of there before it confuses me. Okay, I'm going to kind of leave the left side and not worry about it right now. Okay, I'm going to worry about this one. So I need to be careful. This is really a times x squared plus 14x plus 49 when I FOIL that one out. This one's going to be b times x squared plus 7x, and this one's still just cx. Okay, distributing. I get ax squared plus 14ax plus 49a. Then I get bx squared plus 7bx. And finally, cx. I'm going to group all my x squareds together. I think there's just two, ax squared and bx squared. I often write my little lines to make sure I use them all at least once. My x terms, I have a 14ax, I have a 7bx, and a cx. All right, and then what have I not used? Just that 49a. All right, that means that x squared is factored out of a plus b. That means x is factored out of 14a plus 7b plus c. So out of those three, right? And then that leaves me 49a. All right, I'm going to take it back to 3x squared plus 49. Okay, now this is where we need to be careful as we go to set up our system, okay? Whatever's with the x squared goes with my coefficient with the x squared. They're equal. So here I have a plus b equals 3. Okay. Now I have all this with x, but I seem to be missing an x term here. That means it has a coefficient of 0. So all of this, 14a plus 7b plus c, as much as we'd like it to disappear, we just need to know it equals 0. Even though there's nothing there, we can't make it disappear. It just needs to equal 0. And then thankfully, once again, you don't always get this way. We know 49a is going to equal this constant over here, which is 49. It makes it super easy for us. A equals 1. I'm going up to my top equation. 1 plus b equals 3. So that means b equals 2. Now I'm going to use my middle equation. I have to use everything once. So I get 14 times a, which is 1, plus 7 times b, which is 2, plus c equals 0. That's 14 plus 14 plus c equals 0. 14 plus 14 is 28. If I move it to the other side, I get c equals negative 28. All right, that's what I get. Those are my 3, okay? So I have all my coefficients. I have basically all my constants, right? So I am ready to write my decomposition fraction of, and if you want to, you can write out the whole thing. 3x squared plus 49 on my other page. I did not have enough room. Times x plus 7 squared equals, well, above my x needs to be my a, so that's 1 over x. Above my x plus 7 needs to be my b, which is 2. And above my x plus 7 squared is my negative 28. Okay? Just a quick note, there are times right here, if you look at this, I could just put minus 28 over x plus 7 squared. Okay? Or you can do the plus all the time and just put the constant up there at negative 28. Okay, so there again, that's this. By the way, let's say, because I told you maybe this is by itself, or maybe the x plus 7 is the only, squared is the only one. If that was not needed, you'll get a 0 for that and it'll disappear. So just trust your numbers to get you the answer you need at the end. If you get a 0 for one of your numerators, then that fraction's gone. Okay? All right, moving on to example 3, another scenario for us, okay? Notice everything's factored for me. If you look at x squared plus 2x plus 2, are there factors of 2 that add to make 2? No, that's not factoring anymore. That's all factored for me. I have 2 factors in my denominator, but notice one of them is a quadratic. Okay, so this is my third scenario. So when I go to write my fractions, so my denominators here are x plus 1 and x squared plus 2x plus 2. Okay? So my first fraction, because it's linear, still gets an a. Linear meaning that that x doesn't have a power. But on my second equation, or second fraction here, because I have an x squared, that whole polynomial is a quadratic because of the x squared. I can't just put a b on top. What I have to do is it could be linear on top, 1 power less. So I'm going to put a bx plus c. So it could have a linear part, the x part, and a constant part. So I get both of those up there. This is what happens when I have a quadratic. Okay? Quick side note, we're not going to do it, but just so you understand where the process is, let's say I'm way up here in the corner, okay? Let's say I had an x cubed plus 7. Okay, I need to have a term. I can't have just x cubed. If that's the case, I would need like a bx squared plus a cx plus a d. So if you had a cubic in the denominator, you have to have every power less than that represented above in the numerator to be able to figure out if everything's there. And remember, something might end up being a 0 and it disappears, but we have to put that placeholder in case it's there. Okay, so back down to number 3. We have our two denominators split. We have our numerators with our constants up there, our a, and then now our bx plus c. We're going to multiply times its common denominator, which is the x plus 1 times the x squared plus 2x plus 2. Okay, so denominators on the left side cancels with what we're multiplying by, and I'm left with 5x squared plus 6x plus 3. Okay, on my first fraction, my x plus 1's cancel, and I'm left with a times my x squared plus 2x plus 2. On my second fraction, my x squared plus 2x plus 2's cancel, so make sure this is in parentheses. Bx plus c is still multiplied times x plus 1. Okay, so I multiply my entire equation by the common denominator. The denominator's canceled, and whatever didn't get canceled has to stay on top and be multiplied. All right, algebra time, and it's algebra on the right side right now. So I am going to distribute this a through, so I'm going to get ax squared plus 2ax plus 2a. On the right side, I have two binomials. I need to FOIL that, okay? So don't forget, I'm going to FOIL right here. Bx times x is bx squared. That takes care of my first. On the outsides, I have bx times 1, which is bx. On the insides, I have c times x, which is cx. And last, I have c times 1, which is just c. Okay? So careful on your algebra, because that's going to be a big problem if we're not real careful on our algebra on these, okay? All right. I need to group my x squared. So I have an ax squared and a bx squared. I use those two. Those are all my x squareds. So important that you multiply and you get every little detail down, put your squareds in there and stuff, because if you forget one, it's going to mess you up. All right. Sorry for that interruption. Okay. Then I'm going for my a's, or my x's, I'm sorry. So I have a 2ax, a bx, and a cx. All right. Now my non-x terms, I have a 2a, right? This one right here. And a c. Okay. I think I used all of them. 1, 2, 3, 4, 5, 6, 7. I had 7 terms. 1, 2, 3, 4, 5, 6, 7. Still have 7. That's good. So I think I have them all ordered. So in the first two, I'm going to factor out the x squared and be left with a plus b. All right. The next 3 all have an x. So I'm going to factor off the x and be left with 2a plus b plus c. And then finally, I have the 2a plus c at the end that are my constants. All right, I'm ready to pair this back up with my 5x squared plus 6x plus 3. All right, for my system, a plus b has to match with whatever is touching my x squared over here, which is 5. All right, 2a plus b plus c has to match my coefficient of my x, which is 6. And finally, my constants over here without any x's, so that's 2a plus c, has to match my constant over here, which is positive 3. Okay. Now, this is the first time we had a system that one of the variables wasn't obvious to begin with. Okay. So we kind of have to figure out what can we do to solve our system. Well, my first equation is missing a c, so that's okay. My last equation's missing a b, and of course my middle equation has both. What if I take my first and second equations and I work on getting rid of a b, and then I can use it with my third equation that doesn't have a b. So if I make my top equation just negative a minus b equals -5, and join it to my second equation there, which is 2a plus b plus c equals 6, I can join it. Negative a and 2a makes just a. My b's cancel. I get a plus c equals 1. Now I can take this new equation with my third equation. It's always important we use all the equations as we work. And I can work to get rid of the c's in those two. So I'm going to leave that one from the left the same. 2a plus c equals 3. I'm going to change all my signs to opposite on the second one. Negative a minus c equals -1. 2a minus a is a. C minus c cancels. 3 minus 1 is 2. Okay, so I have my a of 2. Now I'm going to plug it back in to any equation I want to find my b. I'm going to take that, the top equation, a plus b equals 5. So I'm going to get 2 plus b equals 5. That will make my b equal 3. And I'm going to use that, the 2a plus c, right? So 2 times 2 is 4 plus c equals 3. So subtract the 4, c equals -1. Okay. I have my 3. Now I need to rewrite it. Now remember, this is going to look slightly different than what we saw before, okay? So as I rewrite this one, okay, I get 5x squared plus 6x plus 3. That's what I had on top of x plus 1 times x squared plus 2x plus 2. Okay, I'm breaking this down, decomposing it. It was with a fraction of 2 over the x plus 1 plus my b has a 3. So 3x, that x is part of it, plus, or actually it's not plus c, it's going to be -1 because c is negative, all over my x squared plus 2x plus 2. Okay? So there's my fraction, my decomposed, okay? It broke it down into there. And notice I have that linear on top of that quadratic, okay? All right, one more example here. Though my guess is you could probably stand a few more examples, but I do want you to kind of practice some of these on your own. All right, we're going to try to get as much room as I can here for this last question. Notice on this one, I once again have a quadratic of x squared plus 4, but it's repeated, okay? Because it's that whole quantity is squared. That means maybe it's just once, and then it's definitely twice, okay? So that means I break this down into an x squared plus 4 and an x squared plus 4 squared, okay? Because both of these terms are quadratics, I need an ax plus b on top of the first one, a linear on top of the first one, and a linear on top of the second one, which will give me a cx plus d, okay? Every time there's a quadratic as my denominator, I have to have a linear as my numerator. I'm going to multiply the whole thing by its common denominator, which is x squared plus 4 times x squared plus 4. You can write it as squared, that's fine. I just want to make sure we kind of understand what we're really saying. So when I multiply my first equation, or my left side there, with its common denominator, I'm left with x squared plus 2x plus 3. Okay, on the right side, my first one of the x squared plus 4's cancel. The other one needs ax plus b to multiply by the second x squared plus 4. Now, thankfully, at least in this example, on my last term, both x squared plus 4's cancel with that x squared plus 4 squared on the bottom, and I'm just left with cx plus d. So I get saved a little bit there with my multiplication because there's nothing that needs to be multiplied times that numerator. Okay, once again, I'm going to kind of ignore the left side for a little bit, except I'm going to clean it up because I keep putting this random end parenthesis on, but not the other one. And I'm going to work just with the right side. My first two right there need FOILed. First times first is ax cubed Then I have ax times 4, that's my outsides, are 4ax. My insides gives me bx squared, and my last two give me 4b. And then, of course, I have cx plus d that nothing's happening to them, so they're just hanging out there. Okay, I need common terms together. The only x cubed I have is ax cubed, so nothing's with that. Well, this is interesting. The only x squared I have is bx squared. And then the x's, I have two of them, right? So I have a positive 4ax plus a cx. And then for my constants with no x's, I have plus 4b plus d. Okay, so let's see. Ax squared is the only x squared, or x cubed, I'm sorry. Bx squared is the only x squared. I can pull out an x off of these two and be left with 4a plus c. And then my constant, if you want to, you can put a parentheses to say both of those go together. And this equals my x squared plus 2x plus 3. Okay, time to write our system of equations. So in front of my x cubed is an a. I don't have an x cubed over here, so that must mean a equals 0. Well, that makes it easy, okay? B is the only thing in front of my x squared, which is that invisible 1. So I know b equals 1. That's done. All right, but in front of my x is a 2, and with this x is 4a plus c equals 2. And then finally, my constant at the end matches this constant, 4b plus d equals 3. Okay, now keep in mind, this system technically has 4 variables. Okay, so we could be looking at a really big system to solve, but thankfully, we already know our A, we already know our B, and it looks like it's not going to take a lot of work to solve for my C and the D because of the way these broke down. So using this next equation, I'm going to plug in my A of 0 plus C equals 2. That means 0 plus C equals 2, C equals 2. That made it nice. Into my last equation, I'm going to plug in my b of 1. So 4 times 1 plus d equals 3. So I get 4 plus d equals 3, subtract 4, and d equals negative 1. Okay, so I have all my equation or variables now, and I'm ready to decompose that top equation. So x squared plus d 2x plus 3 over my x squared plus 4 squared equals. Remember that a is 0, which means that x is gone. There just is nothing. But I do have a b of 1, so that first equation only has a 1 over the x squared plus 4. Plus, I do have a c of 2, so it's 2x. I do have a d of negative 1, so I'm going to put minus 1 over x squared plus 4, the quantity squared. And there is my decomposition, that fraction broken down. Okay. It's a lot of algebra. The systems by themselves take some algebra, but this decomposition, you really have to watch your fraction work, okay? If you slip up with signs, if you leave off a number, if you leave off a term, there's a good chance that your system's not going to come out real cleanly, okay? But you have to kind of work with it. Heads up, there is a chance you get a fraction here or there. You can work with it. Doesn't mean you were wrong. It means that there's a fraction. That's life, okay? But it's super important that you practice some of these. Bring me some questions to class. Make sure that you're checking with me to say, you know, I'm feeling comfortable, I'm feeling not, okay? So I really want you to start this first day by going to page 765 in your book and trying some of these 3 through 39. Notice I put odd multiples of 3. That's 13 problems from 3 through 39. And I'm not even asking you to do all of them. So like 3, 9, 15, 21, 27, what is it, 33, 39, that's 7 problems. That's not that many. And all their answers are in the back of the book. So you know when you're done if you're okay or not, okay? Try them. It's super important that you have the practice. Let me know if you have any questions.